Hi everyone, Mr. Markwick here. In today's video, I'm going to be showing you how to create 2, 3, and 4-step connectivity matrices. The last video I did on matrices, or modeling with matrices, was creating a connectivity or adjacency matrix from a network. There is a link to that video in the description, so if you want to watch that, please have a look there. But I will be going through that process again in a minute with this example. It is important to be able to draw a one-step connectivity matrix from a network in order to create the 2, 3, and 4-step connectivity matrices. This network here has 5 nodes, A, B, C, D, and E. The one-step route from each of those nodes to the other nodes is represented in this connectivity matrix, which is a 5 by 5, so 5 rows and 5 columns. And to convert that into a 2-step connectivity matrix down here, what's happened is this matrix has been squared, okay? I'm not going to go through the exact maths that we use to square matrices. You can see that obviously, for example, this element here in the first row, the second column, which is a 1, in the 2-step connectivity matrix, the same element is also a 1. 1 squared is 1, but 0 squared is not 1. 0 squared is not 2 in that case there. So there is a process. I'm not going to spend too much time, or in fact any time, going through how that works. I'm going to be using the graphics calculator, but it's not as simple as just squaring each individual element within the connectivity matrix, okay? Anyway, this 2-step connectivity matrix shows the number of 2-step connections from a starting node to a finishing node. So for example, if we look at a specific element, let's look at the 2 here, which is in row 1, column 4, says that there are 2-step connections from node A to node D, okay? A being the first row and A, B, C, D being the 4th column. So there are 2-step connections from node A to node D. Where are they? From A to D. My first 2-step connection is from A to B to D. That's 2 steps. Okay, I've got it on 2 arcs. And the second one is from A to E to D. Again, I've gone along 2 arcs to get from A to D. Okay, so those are the 2-step connections from A to D. Now that's what we're going to be doing here. In order to actually determine how many 2-step, 3-step, or 4-step connections there are within a network, we need to be able to draw the 1-step connectivity matrix first. That's the most important thing. So I'm going to go straight into this example, looking at this network here and drawing a connectivity matrix here. So there are 4 nodes, A, B, C, and D. So I'm going to be drawing a 4 by 4, 4 rows and 4 columns matrix. So alphabetically, A, B, C, and D will represent my first, second, third, and 4th row. Likewise, A, B, C, and D will be represented in the 1, 2, 3, and 4th columns. So what are we looking at? From A in this first element, row 1, column 1, the number of 1-step connections from A to A. There are no 1-step connections from A to A, so that is simply a 0. From A to B, there is one 1-step connection, A to B, so I'll put a 1 in element row 1, column 2. From A to C, there is also one 1-step connection, and from A to D, we can't get from A to D in 1 step, so 0. From B to A, there is one 1-step connection. From B to B, there are no 1-step connections. Now, from a node to itself, you basically would have to see something like this, okay, for there to be a 1-step connection from a node to a node. We don't have that in this network, so that's a 0 there. From B to C, there are no ways of getting from node B to node C in 1 step, so that's a 0. And from node B to node D, there is one one-step connection. From node C to node A, we can't get there in one step. The arc here is showing an arrow of or a direction of travel in the opposite way, so I can't go from C to A, so 0. From C to B, there is no way of getting from C to B in one step. From C to C, again, 0. From C to D, there is one step connection there, or route. From D to A, we can't get there in one step, 0. From D to B, okay, we can get there in one step. From D to C, okay, again, we can't go this way because the direction of flow or travel is not allowing us to go from D to C. And from D to D, again, no one-step connection. So this is the connectivity matrix for this network. Now, to come up with a three-step connectivity matrix, which shows the number of three-step routes within this network from a specific node to another specific node, we simply cube our connectivity matrix. Now I'm going to show you how to do that on the graphics calculator. As I said, I'm not going to go into too much detail at all about what's actually happening in terms of the maths. Sorry. So there are a few ways of doing it. You will need to use though the run or matrix function, which is the first option there. So head into that. You can input a 4x4 matrix here, and you would specifically do that when you're reusing that matrix. And I'll show you how to do that in my next video. But for today, I'm going to show you how to do it just in the run function. So click on Math F4, Matrix in vertices F1. Then we're going to, because there are no 4x4 matrix already ready to go, I'm going to tell it the number of rows and columns, M and N. Again, yep, 4x4, perfect. So let's just press execute for that. And then I'm just going to import my values, the zeros and ones from this matrix into this on my graphics calculator. So 0, 1, 1, 0. And then we are going to cube it to come up with our three-step root matrix, so to the power of 3. And this is then my answer. So my three-step connectivity matrix. Excuse me, guys, I'm going to have to go back to that again. 3, 101. So that's it. That's our three-step connectivity matrix in this network. Let's break it down a little bit just before I wrap up the video. Let's look at some of the elements. For example, this 3 here in row 1, column 2, tells me there are three-step connections or three-step routes between, from route A to route B. In fact, let's actually write those down and color code them a little bit. So there are 3 ways to get from A to B in 3 steps. These are the 3 ways. First of all, I can go from A to C to D to B. It seems like a sensible one to me. So A, C, D, B. You can see the 3 steps. We could go from A to B, back to B, back to A, and then back to B again. It doesn't seem very efficient to me, but it is a 3-step route. So A to B, back to A, and back to B. Notice the difference between the red one there being a path and the blue one here being a route. And the final one, if I do that in green, is from A to B, B to D, and D to B. So A, B, D, and B. Now this is where I'm going to quickly talk about the limitations of these 2, 3, and 4 step connectivity matrices, because really there's only one step there that's really efficient. Like for example, if you're a if you're a delivery man, you're starting at node A and you're ending at node B, you've got to do some deliveries along the way. It would make sense that you follow that red path. Okay, you go from A to C to D to B, because you're not backtracking, you're not visiting a node twice, or you're not visiting a certain location twice. Okay, so that is in this case the only path. The other two routes, you're actually going to the same node more than once. So in the blue example, you actually start at A, you go to B, you go back to A, and then finish at B. So you're actually only traveling to 2 nodes. You're backtracking quite a bit. And in the green example, again, another route, not a path, you're going from A to B to D and then back to B. So it's quite inefficient. So the limitations of 2, 3, and 4 step connectivity matrices are, yes, they tell you the number of, or the total number of routes. They don't tell you the total number of paths. So therefore, they don't really take into consideration how efficient each of those routes are. In this case, the most efficient one, depending on the situation, is the red one from A to C to D to B, because you're not visiting a node more than twice. And the other two, you are backtracking. You're going to a node more than twice, so it's not as efficient. Okay, so that is the limitations. Before I wrap up this video, let's just look at some zeros and some ones perhaps. So in this case, the 0 here in row 1, column 4, tells me that there is no way of getting from node A to node D in 3 steps. Okay, I can't get from A to D in 3 steps. I can actually, if you look at it, I can actually get there in 2 steps. Okay, A to B to D, but I can't get there in exactly 3 steps. Okay, my next video I'll be looking at, adding connectivity matrices to 2-step and 3-step connectivity matrices to say, right, how many routes are there from, for example, A to D that are at most 3 steps. In this case, there would be 1, which is a 2-step path. But in this case, there are 0 routes that take 3 steps from A to D. Okay, again, another little bit of a limitation. The final one, let's quickly look at another value. Hopefully this is all making a bit more sense now. But for example, this one here in row 4, column 3, says that there is 1 3-step route from node D to node C. So I can get from node D to node C in 3 steps, 1 possible way. And that would be going from D to B to A and then down to C. So those are the 3 steps I would take to get from D to C. They're the 3. That's represented just by that one. And that's the only way in this network to travel from D to C in exactly 3 steps. Okay. Hopefully that helps and explains a little bit about the 2, 3, and 4-step connectivity matrices. Basically, what you do if you're looking for 2-step connectivity matrices is you're squaring the connectivity matrix. Here I cubed it in this example. Or if you're looking for 4-step connectivity, if you're looking for 4-step routes, then you would obviously raise your connectivity matrix to the power of 4. Okay, and that would give you the number of routes or paths that take exactly 4 steps to get from a certain node to another node. All right, guys, thanks for watching, and hopefully that helps.